All right, so this is section 10.3. This is really going to cover three different concepts. The first concept is resonance, the second is electronegativity, and the third is formal charge. Now, resonance is a way of talking about basically a molecule can be drawn in two or more ways. And so, hypothetically, a molecule could be drawn in two or more ways, and neither one of them, each of those two representations, each of those two molecules are both right and wrong. Now they are equally right as they are equally wrong. And so resonance gives us the idea that, well, it's not actually either one of them that's correct, but instead it's an average of those two depictions that is most correct. Okay, so electronegativity is the next concept that we're going to get into, and formal charge is the final one, but I'm going to tackle those whenever we get to them. Now, first and foremost, though, I want to get into resonance. The way that we're going to get into resonance structure is we're going to look at the molecule NO2. Okay, so now NO2 minus is nitrite. Okay, this is a polyatomic ion. Nitrogen's rolling in with 5 electrons, 5 valence electrons. Oxygen, there are 2 of them. They're each rolling in with 6. So we've got a total of, well, that would be 5 plus 12 plus 1. That gives us a grand total of 18 electrons to draw. Okay. Now, our first atom that's listed is nitrogen. And to flanking that, I'm going to put an oxygen on each side. Okay, I've got to draw a total of 18 electrons. I want to complete this guy right here. And then I want to complete this one right here. So this depiction right here, I'm looking at a total of 6, 8 electrons, 10, 16 electrons. So I haven't drawn enough electrons. Okay, so then what I want to do is I want to go ahead and do this. Now, does nitrogen have a satisfied octet? No, it does not. So then what could I do? I could take these 2 electrons and drop them in here. And so now my kind of second draft, I'm going to say boom, 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 a double bond. Oh. Okay, so now let's look at these electron totals. We've got 4 from the shared pair, 2 as a lone pair on top of nitrogen, plus 2, plus a shared pair, plus 6 as 3 lone pairs. So that would be 8 plus 2, that's 10, plus 2, that's 12, plus 6, that's 18 electrons. So this is 18 electrons. Everything's got a happy octet, we're good to go. But one detail that's important about this is I drew the double bond on the left-hand side. Does that matter? It absolutely does. Okay. Now, what does that mean? That means that by drawing it on the left-hand side, well, I've kind of placed it. And so if I compare that to, well, this structure right here, are these the same? They both have complete octets for every single atom. The difference is the placement of that double bond. I've drawn it on the left-hand side versus drawing it on the right-hand side. And so what I was getting at a little while ago of them being equally right as they are wrong, well, that applies here. Both of those depictions are correct. They're also both incorrect. So they're like a decent representation. Oh, and I forgot to do my bracket. Let me go ahead and do that. It's the last detail, because this is a polyatomic ion. But it's important to because there are these two representations, well, they're both right and they're both wrong. And so what I end up with is basically two models for this one molecule. And alone, one is not right because of the fact that resonance states that, well, the actual structure is an average of these two different structures. So these are examples of what are known as resonance structures. And one of the things that you'll see from time to time is rather than those two structures, you'll see what's known as a delocalized or a resonance hybrid, which shows where those electrons effectively can be, and it looks like this. I'll draw my general framework, and then what I will do is I'll put brackets, I'll put the constant, and then I'll put a dashed line between these guys. Nitrite presents a little bit of a challenge because of the fact that, well, I still have to juggle the lone pairs of electrons on each of my oxygens. We'll see in our next example how to draw a resonance hybrid. But effectively, resonance structure is a combination of proposed or reasonable structures for a molecule. Now, here what we've got, this was not the nitrite ion, typo, this is the carbonate ion. Now, the carbonate ion, let's go ahead and get our total number of electrons. We've got 4 from carbon, we've got 3 oxygens, each bringing in 6, so that's 18. And then we got 2 more electrons, so we're talking about 4 plus 18 plus 2 equals 24 electrons to draw. Our central atom is going to be carbon. Our adjacent atoms are oxygen, oxygen, and oxygen. Complete the octets of each one of these. Bracket around this whole thing with a 2- charge because it is a polyatomic ion. Fundamental problem with this structure as it is so far, carbon doesn't have a complete octet. How many electrons have I drawn? Well, I've drawn a total of 24 here. To complete my octet, I'd have to add 2 more electrons on my central atom, but that's not going to work. So I'm going to erase that. That's not going to work because I'd have to draw 2 more electrons, putting me at 26. So then I drop those electrons in there, and okay, so now, well, carbon now has a complete octet. I've drawn 24 electrons. I'm feeling good about this, but the problem is now I've got those electrons up rather than to the left or to the right. And so, well, could I rearrange these electrons and put the double bond here? I could, but that's just as right as the last structure. And so there are a total of 3 different orientations for this molecule. This is a great example of how you can draw a resonance hybrid, and that would be something like this. Carbon, dashed line, -2 charge, and then whenever you do that, that goes ahead and we've got we can kind of, what's regularly done in these resonance hybrids is you omit drawing or completing the octet around the adjacent atoms. So what I want you to take away from this, and what I want you to take away from resonance structures, is a resonance structure is the average of however many possible structures that you can draw. And so here we've seen the carbonate ion where we could put the double bond, let me just get that up again, we could draw it here, we could draw it here, or we could draw it here. So there are 3 different representations. All right, so that's the concept of a resonance structure, and that's how I wanted to go into it. The next concept I want to talk to you all about is electronegativity. Now, electronegativity is a measure of how much an individual atom within a molecule wants shared electrons. So it's not going to be a 100% equal sharing. Instead, the more electronegative element, the more that those electrons are attracted to one of those nuclei. So in general, electronegativity increases from the left side to the right side of the periodic table and from the bottom to the top. So the most electronegative element, most E negative, is going to be fluorine. This is a simplification of what's known as the Pauling scale of electronegativity. This is the electronegativity of main group elements. Like I said, fluorine has the greatest electronegativity with a measure of 4.0. Everything below that, or everything else, is going to be lower than 4.0. But these are the relative measures. Okay, so 0.7 is francium, and that's effectively the lowest. So electronegativity and the central element or the central atom of a molecule. An element with a high electronegativity pulls shared electrons closer to it than an element with low electronegativity. Thus, elements of high electronegativity are less likely to share electrons and are less likely to be central atoms in a molecule. In a situation where two elements have the same number of valence electrons, select the one with the lower electronegativity to be that central atom. So lower electronegativity. What we were talking about a little while ago when we were selecting the central element, we looked to the farthest to the left of the periodic table, which coincides with the lowest electronegativity. Okay, so if we look at what's the central atom of POBr3, well, here's the electronegativity values. We've got a winner, phosphorus, 2.1. I don't expect you to know these numbers. These would be provided to you. This is just a rule, which one's going to be the lowest one, and place it. One other thing that you'll notice is what's the first element? What's the first atom element listed? Phosphorus. So we had two ways of picking phosphorus as our central atom there. Okay, the last thing that I want to talk to you about is formal charge. And so this kind of goes alongside electronegativity, but puts a little bit of a check on it. So resonance structures. So resonance is this idea that you can draw multiple structures and they're all equally good, but formal charge is your mechanism to say, okay, I've drawn 6 different structures. Are they all equally good? Is there one that's better than the other? The examples that we looked at a little while ago, well, it was carbonate, which is carbon surrounded by 3 identical oxygen atoms. And I contrast that with, well, if it was surrounded by 2 oxygens and 1 chlorine, would the fate be different? Would something be different? And it would. So we use formal charge to decide which structure or structures is the better representation of the real molecule. So formal charge is calculated by saying for valence electrons minus shared electrons divided by 2 plus the unshared electrons. Now, most likely Lewis structure has, and this is kind of a guideline and a rule, have a small or 0 formal charge, especially that central atom. Most likely Lewis structures have negative formal charges associated with elements of higher electronegativity and have positive formal charges associated with elements of lower electronegativity. Formal charge helps to determine which possible structure is most energetically favorable. I think the best way to attack this is to draw a molecule and draw the resonance structures of dinitrogen monoxide, which is N2O, then use formal charge to determine which structure is more likely to resemble the real molecule. Okay, so we've got N2, 2 nitrogens, 5 valence electrons each, plus 6. We got 16 electrons. Our central atom is going to be, well, N2O. What we have there is we're going to have a nitrogen as our central atom, lo and behold. Okay, so here's one. One nitrogen going to oxygen, and then going to another nitrogen. Okay, now the next part of this is, let's go ahead and place all our valence electrons. We gotta place them around our outer atoms. Done. We've got 6 plus 2 plus 2 plus 6. That's 18 electrons. This representation right here is toast right off the bat. Okay, so now let's go ahead and see if we can tweak it a little bit. Okay, so we've got too many electrons drawn. So if we draw too many, if we've got too many electrons that have been drawn and we don't have a satisfied octet on our central atom. So let's go ahead and try something like this. Drop those in there. Drop these in here. Now let's go with N. Boom, boom. A double bond. Nitrogen, double bond, oxygen. Okay, so now I've got 4 plus 4 plus 4 plus 4. My numbers are coming from, I've got this 4 for lone pair, 2 shared pairs, 2 shared pairs, 2 lone pairs. 16 electrons. Okay. Now, that's all good and well, and that's one reasonable way to draw this molecule, but following a little bit of a different idea, let's see if we could position things a little bit differently. Try using, so here what I've done is I drew 1 shared pair of electrons between my 2 nitrogens, 3 shared pairs of electrons between my nitrogen, my central nitrogen, and my oxygen. Now let's go ahead and complete our octets. My central nitrogen has a complete octet. It's good to go. My oxygen now has a complete octet. My adjacent nitrogen now has a complete octet. I've got 6 plus 2 in this lone pair, plus 6 in this triple bond, or these 3 shared pairs, and then plus 2. That'd be 16 electrons. Okay, so now I have 2 reasonable structures. N, draw my double bond, or a double bond, N. And then a double bond, and then lone pairs. Okay, so now between structure, and I'm going to label them A and B. Which one's best? And actually, heck, looking at A, I could come back with C, where I've got N, got that right there. Okay. So to determine A, B, or C, which one is best? Well, I've got to go through this formal charge calculation. Okay, so the first thing that I'm going to do is I'm going to look at my formula for formal charge. And the way that I'm going to do that is I'm going to say, looking at this nitrogen's formal charge, I'm going to say my valence electrons, which is 5, minus the number of shared electrons, which in this case, I have 1 shared pair of electrons, so that would be 2 divided by 2, and this is in parentheses. And then I'm going to add to that my unshared pair of electrons. I have a total of 6 unshared electrons. So the formal charge for this nitrogen in model A is going to be 5 minus 2 divided by 2, which is 1, plus 6. So 5 minus 7, which is equal to -2. So I'm going to write -2 over this. Okay, now next up, I've got to figure out the formal charge for each one of my different atoms. Okay, so this guy right here. Same formula. Valence electrons, 5, minus shared electrons divided by 2. This has a total of 8 divided by 2 plus my unshared pairs of electrons, which was 0. That's going to be 5 minus 8 divided by 2, which is 4, 1. So I'm going to say plus 1. Okay. So already, if you remember the rules, the idea was you wanted to get as few charges as possible, or you wanted any of those charges to equal 0. Right now I've got 2 atoms, and each one of those atoms has, well, a charge on them. And my net charge for this right now is -1, because I've got -2 plus 1 minus 1. Okay, so now my oxygen, this last atom. Valence electrons. Oxygen brings in 6 valence electrons minus shared electrons, which would be 6, because I've got 3, and I'm going to divide that by 2. So 6 divided by 2 is 3, plus, and then my unshared electron, which is 2. So that would be 6 minus 6 divided by 2, which is 3, plus 2. 6 minus 5 is plus 1. Okay, so now when you look at this, we've got a -2, a plus 1, and another plus 1. So the overall charge for this representation is 0. So I'm going to write my OC equals 0, which is what we wanted for this. But let's go ahead and let's look at our other models. This guy, nitrogen's bringing in a total of 5 valence electrons minus shared, which is going to be 4 divided by 2, plus unshared, which is 4. So that's 5 minus 2 plus 4. And that would be 5 minus 6 is -1. Okay, so that is a little, that nitrogen is better off than the nitrogen in model A, but we got to care about our overall charge. Okay, next up, this one. 5 minus shared would be 8 divided by 2, plus 0 unshared would be -1. Okay. Then the last one, oxygen, 6 minus shared electrons is 4 divided by 2, plus 4. So that would be 4 divided by 2 is 2, plus 4 is 6. So 6 minus 6 is 0. And so that would mean that this molecule right here, although it has lower charges, this has a -2 overall charge, which is not what our molecule has. Our molecule has an overall charge of 0. So I'm going to go ahead, I can look at that model B and I can put a frowny face. Now the last one. Okay, nitrogen, 5 valence electrons minus. Shared electrons is 6 divided by 2, plus unshared electrons is 2. Okay, so that would be 5 minus 3 plus 2 would be 5. That would be 0. Okay, that's an interesting start. Next up, nitrogen again. Now we've got, where are we here? Where are we here? Nitrogen, 5 minus shared electrons would be 8. 8 divided by 2 plus 0. So we're looking at 5 minus 4. It's going to be a plus 1. Okay. So we got an overall plus 1 charge. But what about this single bonded oxygen? This is rolling in with 7 valence electrons. And we subtract the shared electrons, which is 2, divided by 2. Okay. Plus, we add our unshared electrons, which is 6. So that would be a grand total of 7 minus 7, which would be, or sorry, I got confused and flustered for a moment because I realized my math was going to come out wrong. And the reason that it was going to come out wrong is because oxygen rolls in with only 6 valence electrons. Okay, sorry about that. So valence electrons, oxygen's rolling in with 6. Minus, then we've got 2 shared electrons right here, right there. We divide that by 2 and we add that to 6. So 6 minus 7 equals -1. So we've got a negative charge there. So now what we're looking at is we've got models A and model C as the reasonable and appropriate possible answers. B is out of the question. A and C are possible because they both give you an overall charge of 0. This positive charge on our nitrogen is offset by the negative charge on our single bonded oxygen. Now, which one of them is better? Well, we wanted and we want the fewest number of charges. Model A gives us 3 charges. Model C gives us 2 charges. So Model C is the better model and the better representation for the structure of dinitrogen monoxide. There are individual charges, but those charges cancel one another out and give you that overall charge for the molecule. This is a lengthy lecture, but this is a challenging concept, and really it was 3 concepts all rolled into one. So I hope this helped. Practice, practice, practice. You got this, everybody. I know you do. I know you do.